G'day students, welcome to our lesson on walks, trails, paths and cycles. So we're going to learn those definitions. We're also going to learn what it means to be open and closed, walks and trails, etc. Then we'll have a look at Eulerian graphs and Eulerian trails and semi-Eulerian graphs and trails. And then we'll have a look at Hamiltonian graphs and semi-Hamiltonian graphs and investigate a few problems associated with each of those. So if I want to consider Bundaberg area, so here's Bundaberg, I can see that it goes out to Gingin. There's a loop out to Bagara there somewhere, goes down to Childers. There's also Apple Tree Creek, isn't there? So there's another road, the Isis Highway and Goodwood Road, to get out to Childers. So let's just fix that up a little bit. So there's Apple Tree Creek there. There's Childers. You can go out Goodwood Road. You can go out Isis Highway to get to Childers from Bundaberg. Gingin's there. Where else? We can go out to somewhere like Goodnight Scrub or Boyle. Could go out to Biggerdon and Mount Walsh as well. Let's just throw in Maryborough and Harvey Bay as well, and let's talk about Yurong Seeing. That's isolated vertex. So remember, I can draw graphs or maps as a graph. So remember, our graph is a visual representation. Remember, each of those towns we call a vertex. Now, a place like Yurong in the middle of an island is obviously an isolated vertex. If I were to connect it up, that road would be called a bridge, wouldn't it? And that would connect one network to another, for example. What else do we have? We've got a loop out. Here's our loop out near Bundaberg, so that's our Bagara loop. And each road in this case is called an edge. Now we're going to just think about walks to start off with. Now a walk is any sequence of edges and vertices, and so walks can visit towns multiple times or use the same edges multiple times. It's a sequence or any sequence of vertices joined by the edges. Now an open walk is going to start and finish at different vertices, whereas a closed walk would finish at the same vertices. So let's have a look at, first of all, walking out to Bundaberg. Oh, if you were incredibly eager, you could walk from Bundaberg to Childers. Now we just write that as B to C. Now you could then walk up to Apple Tree Creek, so that's B to C to A. Now B to C to A is an open walk. It finishes at different vertices, but if I were to walk therefore back to Bundaberg, so B to C to A and back to B, that would be a closed walk, because it starts and finishes at the same vertices, so same vertice for closed walk. Any trip in a network is called a walk, and we're going to look at two types of walks. First of all, we'll look at a trail. So a trail is a walk without repeated edges. So for example, if someone's starting at A and they want to go for a walk, they can go down to C and then to D and then to E. We just write that A to C to D to E. And what's important here is that no edge, or no edge is repeated. So a trail is for a trekker. They just like to wander around and not repeat edges. Now this is an open trail. If I were to close this up, I would just return to base without repeating any edges. So I would go A to C to D to E to F. So that one is open, and this one is a closed trail. If I want to think about paths, a path is a walk without any repeated edges or vertices. So you think about them more like posties. So a postman might want to deliver to every house on the neighbourhood. So we might go like A to B to C to D to E to F. Now, what did I say? A to B to C to D to E to F. Now that's an open path. We haven't closed it up. So that's an open path. And if I were to close this up, I would just go A to B to C to D to E to F and back to A. So that's a closed path. So this means I just have to put an exception in the rule here. So a closed path has the repeated vertice of A in this one, or the one that you start off with. So the post must get to every house once, for example, so there's no repeated vertices except for the first and the last in a closed path. In an Eulerian graph, you should be able to travel along every edge exactly once and get back to where you started from. So let's give it a go. We might go around the start first. And that works. Yes, so that's an Eulerian graph. So the Eulerian trail is the trail covering every edge of the graph only once. Now, what's important with an Eulerian graph, that you need to count the degree of every vertex. Now, if there's an even number, so 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2, 3, 4, 1, 2, 3, 4, 1 and 2. This is going to work. Now, Eulerian graphs are particularly concerned with edges, and a semi-Eulerian graph will still be able to cover each edge, but we're going to have to make a little bit of a variation to the rule. We're going to need to start at an odd degree vertex. So you can see here that vertex A has a degree of 3. So we'll start at A, and we're going to end up with an open trail. That means we won't come back to where we started from. And the trail of that graph is going to be called the semi-Eulerian trail. And there we go. Now the vertices are what's important with Hamiltonian graphs. So with a Hamiltonian graph, you just want to get around all the way around the graph using every vertex exactly once. Now there's a variety of different ways we can do this. So we could just, for example, go A to B to C to D to E to F to G. Now that would be an open one, and we could close it off that way as well. But what are some other solutions? So we go to A to B to C to G to F to E to D. We've done that as well. Now that's an open one, but we've hit it all exactly once there, haven't we? So that would be a semi-Hamiltonian solution there, because it's an open graph or an open trail, but we've hit every vertex. So let's just run through that again. You want to get around all the way around the graph. Now it's just easy on this one to trace the outside, and that would be our closed trail for a Hamiltonian graph. We've done a lot today, lots of definitions. We've looked at walks. We've noticed that trails and paths are types of walks, and they can be open or closed. We've then looked at Eulerian graphs and trails, and semi-Eulerian graphs and trails. Then we've just finally looked at Hamiltonian graphs and semi-Hamiltonian graphs. When you're done there, please work on your mastery exercises.